Hello, welcome to Rambus Design Summit. My name is Frank Ferro. I'm the Senior Director of Product Management at Rambus, responsible for physical IP. That includes all of our memory IP and SerDes IP. And today I'm going to be talking about our latest memory IP, which is high bandwidth memory. And we're going to look at how HBM enables AI ML. So the growth in data traffic continues to stress our infrastructure. Everyone, is walking around with our phone, and we want instant data, we want instant information, and so that just continues to stress the infrastructure. So one way to solve that problem, of course, is to add more data centers. And you can see here on the charts and some of the statistics that that's certainly one solution that's being used around the world. Where in 2021, last year, 100 new hyperscale data centers were brought online, bringing the total to 700 worldwide. And as we look out into 2024, we'll see an additional 300 being added. So adding more data centers is certainly one way that helps deal with all the traffic. But the volume of data, in adding more data centers helps, but that is of course expensive. Those data centers are power hungry. So we want to also look at more efficient ways of dealing with the data. So, you've got raw data, but there's also data being grown in the network through, how we're processing the information, and with, in particular, with AI, ML, and neural networks. So these AI networks that are being trained are just requiring huge amounts of data. The process we go through is really, you've got is kind of a never-ending loop here. If you see down the bottom right-hand corner, where you've got bigger data sets that are required for these AI ML, you've got bigger models, you need more compute power, and so that you get into this vicious cycle. And you can see that the size of these data sets are growing. As a matter of fact, I even saw an article this morning about a processor that's able to do 20 billion in terms of the data set size. So these, the processors are trying to keep up, but again, you have to look at how you do this efficiently. So certainly get more processing, more memory, but you also want to look at how we efficiently use those. So if you do things, for example, like, let's look at the actual data itself and how we can get better efficiencies out of the data. So for example, if you look at data that has lots of zeros, that you don't have to necessarily store zeros, or you can, if you multiply zero, you get zero. So we call that sparsity. We're looking at the precision of the data stored. So we're again, we've got a lot of data to deal with. We want to process it much more efficiently. And so we're looking at ways to, improve the overall efficiency and performance of the network. So this need for efficiency is driving new architectures. And today, most of the processing is done on the generic CPUs and GPUs. And you can see on the chart here, that's really what's dominating in the market today. And the CPUs are doing a good job, and the GPUs are doing a good job, clearly. But as you get into these very specific neural networks, you're going to want to develop processors that are optimized for those specific neural networks. And that's definitely going to improve the performance, and also reduce the amount of processing or the need for stressing the infrastructure by having these much more efficient processors. And so as you can see, as you move over time, these CPUs and GPUs are going to start getting replaced by more custom processors. And part of those custom processors are going to need to design very efficient memory systems that match up to those networks. And so we want to get a good balance of processing power and of memory bandwidth. Before I go too far, I want to talk a little bit about definition. So I've already thrown out some of these terms of training and inference. So I just want to define those a bit more. So when you have a neural network, you're going to want to train those networks. And the way you get a good network is with lots of data. So if you're trying to recognize, for example, you can see here different images, you're going to want to train that network on, what's a cat or what's a bird or a horse. And then you pump a lot of data into that network and you train it over time. And that could take, days or even weeks to train the network. And then once those networks are trained, then you can kind of push those out into the edge or onto the endpoints of the network. And then that process of recognizing those images we call inference. So training takes a lot of time, takes a lot of data, takes a lot of processing power. Inference is going to be more cost sensitive as you move closer to the end user. And so inference then requires a little bit less processing power. But again, still, we need to have good, efficient engines to do both the training and inference. So what are some of the memory systems that are showing up in these different AI? So if you look on the far left, you see DDR. Now, DDR has been around forever, and it's continued to be the main memory that's used in the servers and PC. And DDR is very good cost efficiency, and that's the good news. And it's very reliable. But on the other hand, the maximum speed of DDR is about 3.2 gigabits per second. Now we're moving into DDR5 finally, which is going to be increasing that up into 8 gigabits. But because of the speed limitation of DDR, other memory technologies have started popping up. So we see mobile memory, LPDDR, which was originally targeted for your cell phone, is now being used in other applications like automotive and even in different AI edge or endpoint applications. And the reason for that is LPDDR has been running at 4.2 gigabits per second, so LPDDR4X. We also see GDDR moving away from its traditional role as a graphics memory, and again, GDR stands for graphics, because GDR is even faster, up to 16 gigabits per second or higher. So GDDR also is an alternative to DDR. And then finally, where we're going to spend our time today is looking at high bandwidth memory. And what high bandwidth memory does, it takes the traditional DDR and now configures it in a 3D stack configuration. So you can see here these kind of purple colored memory stacks. And then these are each of the different DDR memories. You can see 4 in this graphic here. And then you have these sitting on interposer, and then these sit in a package. And the reason you need the interposer is because HBM is a very wide technology. So what you have is the same memory technology that you're going 1,000 bits. And versus, say, if you look at traditional DDR, where you're probably going 64 or 72 bits. So now you've got 1,000 bits that you've got to route from these DRAM to the processor. And now you've got 4 of these, right? So you've got many, many thousands of signals that have to get routed. And so that's why you have this 2.5D technology. So the good news with HBM is you get a lot of processing power or a lot of memory bandwidth in a very small footprint, but you've also got to deal with the 2.5D package and manufacturing. So that does certainly add cost. But for the highest performance, best memory efficiency, HBM is becoming the memory of choice. Just recently, this past January, JEDEC announced a new HBM standard called HBM3, which is roughly the 3rd generation HBM. And again, it's because of the need for bandwidth, JEDEC has been doing a really good job in getting these high performance memories out on a pretty regular schedule. So about every 2 years now, we'll look at that on the next slide, we've been getting speed upgrades on HBM2. So the current HBM3 is 6.4 gig, which is roughly double that of HBM2E. They kept the interface the same as 1,000 bits, but you're getting more channels with HBM3. So you're going from 16 channels to 32 channels. So that does help depending on the type of neural networks you're running. you can adjust the granularity of your data. They've also increased the density. So we've gone to 12 high stacks. That gives up to 32 gigabits of memory. And in the future, they're going to go even higher to the 16 gig stacks. Again, same basic interposer technology, 2.5D. One other thing they did is because the speed is doubling, you want to keep the power down. So the voltages now on the I/O have been reduced down to 0.4 volt signaling, so 1.1 volt and 0.4 on the signaling. So again, trying to keep that you have all this memory in a very small footprint, so you want to try to keep that power profile as low as possible. So again, I think they did a really good job in terms of making the trade-offs to improve the speed and improve some of the DRAM access efficiency and reducing the power. So if you look at the memory standards over the years, we started with HBM2, and that was at 2 gigabits around 2016. And very quickly, the industry moved to HBM2E in 2018. So you can see it was a 2-year bump in speed. And we had customers who were using HBM2, and already, even though you have very good bandwidth at 2 gig, they just needed more bandwidth. So HBM2E came out, or HBM2 came out, E at 3.2, and then eventually it moved all the way up to 3.6 gigabits. And then just most recently, the industry's announced HBM3, which again kind of roughly doubles the speed and performance. And Rambus, in anticipation of the fact that we saw with HBM2E, they started at 3.2 and moved to 3.6 gigabits. Rambus announced the 8.4 gig memory or PHY support and controller support. So we understand the industry needs more bandwidth, and so we want to allow us to, our customers to kind of future-proof their designs by having a PHY and controller that can run over 8 gig as the DRAM industry catches up. So if you look at HBM from a more practical standpoint, typically when you're designing these systems, we talk about, AI, ML training, typically needing around 1 terabytes per second of performance. You can see this kind of orange line here shows you, where from a system design standpoint, you're going to hit that magic kind of 1 terabyte per second, number. So with HBM2E, you can see here you have a configuration that is 2 stacks or 4 stacks. So back with HBM2, you'd need roughly 4 stacks of DRAM to hit that. As we move into HBM2E, now you can you're still kind of with 2 stacks. You can see here in the blue, you're just about there. And then now with HBM3, you're with a 2 stack, you're well over that performance range. So again, depending on the type of networks and the application you're running, HBM3 gives you a lot more flexibility to either cut down on the number of memories that you need, kind of saving some cost, or if you just need flat out bandwidth, you go with 4 stacks or even more. I've seen designs that can put 6 stacks, and you can see here you're up in the 3.2 plus gigabits per second range. I wanted to show you an example of a customer who's using HBM. Customer is called Inflame. They're a company in China, and this is a nice picture they have here of their 2.5D system. They kind of break it out. You can see on the very top here is their SoC, and you can kind of see these 4 HBM DRAM stacks around the SoC. So they've got the chip in the middle. You've got 4 HBM DRAMs. You can see is here you've got the silicon interposer, and then the silicon interposer sits inside a package. So this is a nice breakout of what this 2.5D system looks like. And if you look at their card, these are accelerator cards for the network, and they've got 2 different versions of that card. This is the Cloud Blazer, the T10. This is 80 teraflops of processing performance with 512 gigabytes per second of memory bandwidth and 16 gig bits of capacity. The Cloud Blazer 2 card, it takes the latest HBM2 with HBM2E, uses 4 of those. Now they've got almost 2 terabytes per second of performance, and you can see these are 300 watt cards, so they have the extra power for those. So again, you can take these accelerator cards and use them for applications in the for AI acceleration in the cloud. I wanted to show you just a couple of other examples. You can even, although we talk about training, they have similar cards for AI inference. So if you look at the Cloud Blazer i10 card, a similar kind of performance, 70 teraflops that uses 2 HBMs at 512 gigabytes per second. And so you've got a card that can be used for maybe low-end training or save you a little bit of cost and do inference. Another card, although this is not HBM, I just wanted to show this as a comparison. And I have another talk where we're going to be looking at GDDR6 more closely. But as a comparison, you can also take this card from Acronix and get basically the same performance using 8 GDDR6s, and you get the same 512 gigabytes per second of performance. So in this case, you've got inference cards that can either use HBM or GDDR6. And again, like I said, you can tune into the GDDR6 to learn more about that. So last year, Rambus had announced our 8.4 gigabit. At the time, we called it the announcement HBM3 ready because the standard had not been announced. This was back, I believe, in the summer of last year, and then it was announced this year in January. So again, in anticipation of the standard, we wanted to make sure that our customers could start getting ready for HBM3 and start designing systems as early as possible. So what I'll do now is maybe we can look a little bit closer at the HBM3 solution. So if you look on the picture on the right, this is the HBM subsystem. So you've got two main pieces. You've got the physical layer, the PHY, and the PHY connects to the HBM DRAM, and you've got all the channels here. And then on the other side, toward the ASIC, you've got our HBM3 memory controller. And then the controller talks to the SoC and provides the interface to the DRAM, to the PHY, and then to the DRAM. And we're gonna double click in on both of these pieces and look a little bit more closely at the PHY and the controller. So this picture, as we start to look at the physical design, you can see a cross section of the HBM. So before we've looked at it a couple of ways. We looked at the block diagram, and then we looked at the actual picture back from in Flame. But now I'm going to take a quick look at the cross section of HBM. So you can see here on the left-hand side, you've got the HBM DRAM. So you have all your DRAM slices. This is a 3D stack of DRAM. You've got your through silicon vias, and then you have a logic layer that eventually goes out to the bumps that sits on an interposer package. And then on the right-hand side, we have our system on a chip, and you have your HBM3 memory subsystem. So this is the PHY and the controller. And then the PHY talks through these bumps, the micro bumps through the interposer, and then you have connections to the DRAM. And so this is how the design is. You can try your best to keep these traces close together. You want to minimize your SI effects. Depending on the type of design, you're going to have multiple layers to route signals through. And you've got these signals coming through your power and ground. And then this whole system sits on a package, and then the package sits on a traditional PCB. So the key advantages of working with Rambus is that we're going to provide you the entire system design. So we have the complete memory subsystem, the PHY and the controller. We have the physical reference design to show you how to do this interposer. And we also have a reference design to show you how to do the package. And we're going to talk a little bit more about that as well. So just a quick closer look at the PHY layer. So we have all the features you would expect on the PHY. So again, it supports the data rate up to 8.4 gigabits. We support all the different DRAMs that are available. That's 16 channels and all the different densities. We have a DFI style interface talking to the memory controller. So this is a standard using DDR, and we've adopted that for HBM. That allows us to work with, of course, the Rambus controller, but some companies do their own controller. And so if you do your own controller, you can use this interface. And in some cases, companies even do their own PHYs and same thing. So you can use our controller and PHY independently, or you can take the entire subsystem, which Rambus will deliver and validate for you. The PHY is delivered as a hardened macro, and the controller is delivered as a soft macro. Other interesting features you have, because it's a 2.5D structure, it's hard to get in to see the signals. So you have different types of test modes, like the IEEE 1500 test support. You also have lane repair. So for example, if one of these lanes are broken, you have redundant lanes that you can remap then to get around and work around those broken lanes. We also have a mode called PHY independent mode that allows you to isolate the PHY and the DRAM. And this is a very nice feature when you're doing debugging. So the PHY can talk directly to the controller, the PHY can talk directly to DRAM without the controller intervention. And this is, like I said, great for bring up and characterization and a debug of your system. And then Rambus has a really nice environment called Lab Station that through a JTAG interface, you can get in and look at the system. You can read and write memory. You can use it for debug. You can write scripts. And so it's a really useful environment for doing your system ASIC. Just a little bit more on the controller side now. So if we look and expand the controller, there's a number of soft blocks here in the controller, these lighter blue, and these are very configurable because basically every customer system is just a little bit different. And so you can customize the interface between the controller and your ASIC, whether you use like an AXI interface, or we have a native interface. You can have multi-ports. You can have read, modify, write. There's error correction built in. And so what we do is we work very closely to customize the design so you get the best overall DRAM efficiency. And we've had customers, up into the high 90s in terms of DRAM utilization. So again, we have a test bench environment that we give you, and we work closely with you to tune the controller for your specific data. And the controller also has its own full set of test capabilities as well. So you have your test blocks you can build into the controller. You have your test blocks in the PHY. Again, very useful from both design and optimization of the system. So the last thing I want to talk about is the interposer design. So when you're doing HBM, of course, you've got the physical layer, but very important is how you do the PHY. If you're going the interposer, if you're going to get the maximum performance out of your system. And so what Rambus does is we, as I mentioned, we give you a reference design, but we also work closely with you to look at the specific channel that you're trying to design, and then we work closely to optimize that channel. So we'll run simulations, we'll do different SIPI checks, and then we'll provide feedback as we go through the design process. And if we look at what's changing from HBM2E to HBM3 from an interposer perspective, with HBM2E running a little bit slower, helps in terms of the interposer design. In the case of HBM2 and 2E, you're running interposer stacks that were 3 or 4 layers. Typically, you'd have 2 layers for routing and 1 or 2 layers for ground. But as we get into the HBM3 now, the speed's going up. So we're going to need additional layers in the interposer. So we see designs that are now, greater than 4 layers for HBM2E. We also see from a silicon standpoint an increase in the oxide thickness, and even things like adding capacitors into the decoupling capacitors into the interposer itself. Again, all these things are being added to help ease that kind of SI effort, and to try to help you minimize the crosstalk and the different effects that you're going to see running up into the 8+ gig range. So I want to summarize a bit by just talking a bit about the Rambus's experience. So again, we with HBM2E, we actually delivered the fastest HBM on the market all the way up to 4 gig, although the DRAMs never quite caught up. HBM3 jumped in, but again, we gave good design margin with customers designing HBM2E. So if your system's 3.6, the PHY goes all the way up to 4 gig, and so that gives good peace of mind. Huge number of designs out in the market, over 50 design wins between the PHY and the controller, and we've never had any respin. So silicon's been right the first time. Supporting all the different process nodes, whether it's depending on the foundry you're using. We've built our HBM PHY in all the different foundries. So again, quite a bit of experience in different, and with each of those foundries, you have a different 2.5D flow. So we built chips for the foundries, and depending on the different packaging technologies, we've supported those. The PHY, as I alluded to earlier, is delivered as a hardened time enclosed macro, so that simplifies the design integration. Again, it includes all the PHY IoT caps. So there's no other area, nothing else that you have to add in. And then we also do of course, the controller integration we talked about. And I think that, again, the big differentiator for Rambus is, as a signal integrity company, we're going to work very closely and give you the reference design for the interposer and package, and then we're going to iterate through those designs until we see nice, clean eyes and systems working well. So again, not just a PHY company, not just a controller company, we're going to deliver the entire HBM2E system. So again, summarize, the industry continues to push hard for more and more memory bandwidth to keep up with these AI systems and the growing data sets. JEDEC responded nicely by adding HBM3 now and at data rates of 6.4 gigabits per second. This with Rambus, we've given you a little bit more headroom on that, going all the way up to 8.4. And like I said, I'm sure the DRAM industry eventually is going to catch up. We provide a fully integrated memory subsystem, and along with the full system design of the package and the interposer. So I just want to remind everyone that you can ask questions in the pop-up. So if you have questions, please go ahead and do that. And I want to thank you for listening in to my talk, and look forward to speaking with you in my next presentation. Thank you.